Hey everyone, and welcome back. Today, we are diving into one of the most powerful frameworks in modern data science and statistics: Structural Causal Models, or SCMs. Before we look at any complex equations, let's build a solid, real-world intuition for why we even need them. Think about standard machine learning. Most traditional ML algorithms are incredibly good at finding patterns or correlations. If you feed a model millions of data points, it can tell you that when variable A goes up, variable B usually goes up too. For instance, data from a tech platform shows that customer support tickets and server crashes are highly correlated. When crashes spike, so do support tickets. Now, a standard predictive model looks at a massive surge in support tickets and accurately predicts that servers are probably crashing right now. Mathematically, that prediction is spot on. But as engineers, we know turning off the customer support desk won't magically fix the servers. Deleting tickets doesn't stop crashes. And fixing a server doesn't delete existing tickets. There is a root cause here. A buggy software update. When a bad update deploys, it crashes the servers, and it independently drives furious users to open support tickets. The bad code deployment is a confounder. It drives both events, creating a statistical link between them where no direct causal link exists. It is a mathematical blueprint of reality. It doesn't just state that variables are related. It explicitly defines how nature assigns values to variables based on other variables. Think of an SCM as a series of one-way streets. If A causes B, information flows securely from A to B. But if we step in and manually disrupt or change B, variable A remains completely unaffected upstream. This directional, mechanistic worldview is what separates causal inference from mere curve fitting. And it's the exact intuition behind SCMs. Now that you have a mental picture, let's formally define an SCM. A structural causal model is a triple M equals U, V, F, where U is a set of exogenous variables. These are factors that are not caused by any other variable in the model. They represent background noise, randomness, or unmodeled influences, like genetic predisposition, measurement error, or random shocks. Think of them as nature's dice. V is a set of endogenous variables. These are the variables we are interested in, and they are caused by other variables inside our model structure. F is a set of structural functions. One unique function for each endogenous variable. Each function tells you exactly how that variable's value is determined by its direct causes. Internal variable. There is a corresponding function that maps its causes to its value. Let's dissect this equation carefully. Vi is the variable we are explaining. PAI stands for parents, the direct causes inside the system, and UI is the unique background noise specifically affecting that variable. Let's look at a concrete structural system containing three variables, W, X, and Y. Look at how their equations define their interactions. We map this system directly to a directed acyclic graph. W has no internal parents, so it sits at the top as a root node. Because W appears inside the function arguments for X, we draw a clear, directional causal arrow moving from W to X. Finally, Y takes both W and X as structural arguments, which means Y receives directed arrows from both upstream parents. Now, let's execute an active policy intervention using Judea Pearl's famous do operator. When we write do x equals x0, we are not passively filtering data. We are violently altering the universe's mechanics. We perform structural surgery. We wipe out the natural equation determining X entirely, erasing its dependency on its parent W. In its place, we plant a completely static structural constraint. X is now forced to be a constant. Graphically, look at what happens. Because X no longer responds to its parent W, the arrow flowing from W to X is completely snipped and destroyed. This isolates X from historical confounding, allowing us to accurately compute the downstream survival or propagation of signals to Y under pristine conditions. Let's look at a concrete example. Studying for an exam score. Here, our exogenous background elements U are student ability and raw luck. Our endogenous variables of interest V are hours studied and the final exam score. Our structural equations make this precise. Hours studied is a function of ability and some background random hours, while exam score is directly calculated as 50 plus 10 times ability, plus 5 times hours studied, plus luck. Notice the network structure this creates. Exam score is a function of ability and hours studied, but hours studied itself depends on ability. That forms a mediated chain. Ability to hours studied to exam score, alongside a direct causal effect from ability straight to score. Now, what is the key underlying property? If we fix the exogenous variables, nature's dice rolls, the entire model becomes fully deterministic. Every endogenous variable is uniquely determined. This allows us to mathematically define interventions. We copy a policy step and force a variable to take a complete constant value, shattering its native causal links. For example, we can forcefully mandate that hours studied equals 10 for absolutely every student in the system, completely ignoring their raw internal ability. By cutting that link, we are perfectly simulating a randomized controlled trial. Welcome back. So far, we've looked at infrastructure systems and raw mathematics. Now let's explore an application at the absolute cutting edge of artificial intelligence, using SCMs to fix bias in modern NLP. Large language models are excellent text predictors, but because they train on internet text, they passively absorb human statistical correlation, including systemic demographic biases. To fix this, we have to stop treating text as flat statistical arrays and model the data generating mechanism. Let's look at the true causal graph generating pronouns. In the real world, a person's demographic identity G should causally influence pronouns P, but it shouldn't dictate their career path O. However, historical internet text creates an unprompted causal link from G to O. When a transformer trains on this data, it absorbs the red arrow. It treats occupation text as highly dependent on demographic characteristics, resulting in biased stereotype associations. Traditional models try to hide this by heavily filtering vocabulary words, which degrades performance. Structural causal models offer an elegant math surgery tool, the do operator. Instead of accepting raw datasets, we mathematically intervene on the system by executing do occupation equals constant. We force balance the text samples. Look at what happens to our causal graph. Because the variable is explicitly held constant by an intervention, the historical link feeding into occupation is instantly severed. In engineering terms, this corresponds to generating precise, counterfactual text data mutations. If our dataset contains the sentence, "The male software engineer wrote code," our structural model algorithm automatically synthesizes its parallel counterfactual statement. This isolates the pronoun response solely from true syntactic constraints, successfully scrubbing away historical career demographic confounding.